Hello everyone, my name is Vidisha Joshi. My class is BSc PCM third year regular. My roll number is 225045 and my topic of discrete presentation is finite state automata, types of finite state automata which are DFA and NDFA and transition table. Finite state automata. A finite state automata is a special kind of finite state machine. It differs from an ordinary finite state machine in two respects. First, it has no output and some of its states are distinguished as accepting states. A finite state automaton M consists of a finite set A of input symbols, a finite set S of states, a next state function f from S into A into S, also called the transition function. This is the function which describes change of states during the transition. A subset Y of set S of accepting states, an initial state S0 belonging to S. It is written as M is equals to A, S, F, Y, S0. This special kind of finite state function machine is known as deterministic finite automata, abbreviated as DFA. Since for each pair of state and input value, the next state is uniquely determined by the next state function, that is the transition function. Non-deterministic finite state automation. This is another important type of finite state automation in which there may be several possible next steps for each of input value and state. Such machines are called non-deterministic. A non-deterministic finite state automaton, abbreviated as NFA, consists of a finite set A of input symbols, a finite set S of states, a next state function f from S into A into PS, which is the power set of S, that is the set of all subsets of S, a subset Y of set of accepting states, an initial state S0 belonging to S. The main difference between deterministic and non-deterministic automata is only in F. For deterministic automata DFA, the outcome is a state, that is an element of S, whereas for non-deterministic automata NFA, the outcome is a subset of S, that is in deterministic automata, the next state function is a uniquely defined state, whereas in a non-deterministic automata NFA, the next state function takes us to a set of states. Each NFA accepts a language that is also accepted by some DFA. We can always convert NFA to DFA. Transition diagram. A transition diagram is a finite, direct labeled graph in which each vertex represents a state and the edges are labeled as input or output. Now seeing the following example, Q0 and Q1 as vertex are states and 0 and 1 are input values. Now representing it in form of transition table, for state Q0, for 0 input value it goes to itself, that is Q0. For input value 1, Q0 goes to Q1, and Q1 for 0 input value goes to Q0 and for 1 input value goes to itself, that is Q1. In this diagram, Q0 is the starting or initial state and Q1 is the final or accepting state. Transition table. It is basically a tabular representation of the transition function that takes two arguments, a state and a symbol, and returns a value, the next state. In the transition table, we have rows which corresponds to states, column which corresponds to input symbol, entries which correspond to next state. The start state is marked with an arrow representing the initial state. The final or accepting states are marked with a star. Now to convert the given NFA to DFA. Here we are given three states which are Q0, Q1 and Q2. Now representing the given NFA in form of a transition table, we see for Q naught, for 0 input value it goes to itself, that is Q naught, and for 1 it goes to both Q naught and Q1, and Q1 for 0 goes to Q2, and for 1 also it goes to Q2. Now constructing the table for DFA, for Q naught 0 goes to Q naught and Q naught for 1 goes to Q naught Q1. Now expanding for Q naught Q1 state, we get Q naught Q1 for 0 goes to Q naught Q2, for 1 it goes to Q naught Q1 and Q2. For Q naught Q2 on expanding we see that for it 0 for it goes to Q naught, for 1 it goes to Q naught Q1. Now expanding Q naught Q1 Q2, we see that for 0 it goes to Q naught Q2 and for 1 it goes to Q naught Q1 and Q2. Now from the table we can see that in DFA we have 4 states which are Q naught, Q naught Q1, Q naught Q2, Q naught Q1 Q2. Now representing this table in form of a transition diagram, we can make Q naught, Q naught Q1, Q naught Q2 and Q naught Q1 Q2. Here Q naught is the initial state and Q naught Q2 and Q naught Q1 Q2 are the final or accepting states. We take these two as the final or accepting states because in NFA Q2 was the final states, so in DFA all the states containing Q2 will be considered the final state. This is the transition diagram of DFA. Language accepted by an automaton. Suppose a string of input symbols is fed into finite state automation in sequence. After each successive input symbol has changed the state of automaton, the automaton ends up to a certain accepting or non-accepting. The status of this final state determines whether the string is accepted by the finite state automaton or not. These strings that send the automaton to an accepting side are said to be accepted or language recognized by the automaton. If a string is not accepted, we say it is rejected. A string is accepted by an NFA if there is some sequence of possible moves that will put the machine in a final state at the end of the string. A string is rejected only if there is no possible sequence of moves by which a final state can be reached. The language accepted by a finite state automaton M denoted by LM is called set of all strings that are accepted by M. That is LM is equals to set X belongs to I naught. X is accepted by M. Here I naught be the set of all strings over I. The power of a machine does not lie in the number of strings it accepts, but in its ability to discriminate, to accept some and reject others.